Hello, my name's Kevin. Thanks for the opportunity to talk about something fun in the Wolfram language. So I'm going to be discussing some very basic games made in the Wolfram language and played within the notebook interface. So the talk is organized sort of chronologically in terms of how video games were developed. So the first thing I'm going to actually introduce is a game called Circle Pong. Now, this was actually a winner from the 2016 one-liner competition that Wolfram hosts every year as part of the Wolfram Technology Conference. And this is a modified version of that code because the code is supposed to be done within a tweet on Twitter. And so I've actually extended the code to make it a little bit more readable, but let's just see what the game looks like to start. So what you see is you have a value that increases as it heads towards this paddle, so to speak, which is a crosshairs. And you're rewarded for getting the score, which is also acting as a ball to bounce around. And then the game is effectively over once the score leaves the bounding area. So all games is a fun interface. And Mathematica and the Wolfram language is really good at making interfaces. So some of the principles in making interfaces often revolve around using the dynamic function as well as including everything within a dynamic module. And so that's what I'm going to explain here. If you're not familiar with dynamic, this is effectively a wrapper that the front end, the notebook, understands, in which anything that the dynamic is wrapped around, in this case it's wrapped around this entire graphics element, this inset, it will try to update as fast as possible based on the CPU speed. So very similar to really old computer games that relied on the CPU clock speed in order to actually play the game. So the way that we make sure that values don't leak out into the global context, we also like to scope our variables using a dynamic module. Now what's nice about dynamic module, if you're familiar with scoping in the Wolfram language, we also have the module function. What dynamic module allows you to do, and I'll actually show this by lowering the speed, if I were to copy this output cell and then paste it somewhere else, you'll actually see you get an independent copy of that. So even though I can reflect the ball and the one below, I can play the upper one independently. They actually don't talk to each other. So this is a nice way to limit the scope within the front end. So I know it's not fun really to look at code, but I still want to describe what this code is doing because this illustrates the simplicity of creating games, especially in a system such as the Wolfram language. So you'll see that this is effectively just a graphics, and it consists of just an empty circle, and on top of that we actually inset, which is another graphics primitive, an updating score. And what the inset does is it changes its position, held onto by the symbol ball position, which basically says if the location of the ball is within a certain radius of the locator, which is our paddle, then increase the score and change the direction of the ball based on the score's value. Otherwise, if you're not near the paddle, then just keep the ball going in the same direction, that is, unless you have somehow left the game board, which is only of radius 1. And I did mention that this is very similar to really old computer systems in that the CPU clock speed is really what is updating everything. And so oftentimes what we'll need to do is slow down this update by some kind of artificial speed parameter. So in this case, we're just doing sort of a Euclidean addition of motion. So we're just adding a certain distance, albeit a very small distance, and letting the CPU add it as fast as it can do. And so we're basically lowering the distance added every time step to make the ball seem like it's moving in a smooth, continuous path. So this is a simple game. It was a nice addition to our repertoire of examples, but we can go much more further than this. So one of the other nice ways to make a fun interface is a so-called a point-and-click adventure. I'm not sure how many of you are familiar with video games, but there was a game that came out called Space Quest, made by Sierra, in which you controlled a character, a very pixelized character, because this is an old game. But it was pretty fun. You would go around the map, walking around, interacting with objects using a click interface. And so because it's a point-and-click adventure, Mathematica does have an interface already built in that does this as well, the so-called click pane. And what this click pane does is it interprets your mouse click as a pure function, which is here at the end. And so all I'm actually doing is, as I click, I determine where I am and where I'm going. I have a sort of speed factor that I mentioned before. And then I force every single change to be updated on the screen using the finish dynamic. Otherwise, it would kind of jump ahead at too fast of a rate. So you see in just a few lines of code, I get this kind of funny animated character in a very old pixelated type environment. And so, I mean, this is a demonstration of the possibility of having a point-and-click environment. And it's by no means a finished game, because you can also see that I can jump the floor. It's really just an optical illusion, and I haven't gotten the character to actually change directions in terms of his orientation. So let's continue. So sort of moving forward in time, Tetris is a very popular game that was made, and oftentimes I always encourage, if I'm teaching somebody a new programming language for the first time, to find a project that they actually enjoy, because motivation is easily 80% of the work. So if you're motivated to finish a project, then you'll continue it towards the end as opposed to getting something you don't want to do. So oftentimes I will suggest video games as a common theme to teach someone the language. And in this case, that was also done by Boris here, who had a student, Nikita, and through creating Tetris inside a Wolfram Language notebook, basically got her to learn the language while at the same time creating a nice interface. So this does have sound included, which is how I modified their code, but otherwise the code, which we'll kind of go through soon. Let's see, if I unmute my speakers, I'm not sure if you'll be able to hear this. So the only reason it takes a long time to start is because of the music. But basically, it's a full game of Tetris within a notebook interface. So I'll just end the game pretty quick. So what you see here is basically, again, a graphics object, which you can see by the orange box that's around it. They have a nice preview window of the next tile that's going to come. And if I actually had cleared a line, you would see the score increase. So the game itself is more complicated than the previous examples. So one of the nice ways, again, to limit the scope of the variables that you're using is to put everything inside a package. And so what they start with is this function begin package to start a new context. So none of these variables will leak out into the global space. And then they define a usage statement here, which is necessary in order to cause other variables to be accessible within the global context. Because you see what they do right after this usage statement is they start a private context, which will hide all the variables from the global scope. The only variable they don't hide is Tetris, which is the way that we actually started to play the game. So the only addition I made to this game is actually adding music, where I imported a MIDI file, and then we can play that later. Now this code is a bit more complicated, so I'm not going to go through it in detail, but there is a community post linked above that you can go to. And I think I'll just point out some of the interesting things about their code. The first thing that I want to point out is their coding style, which I thought was pretty nice, is they actually separate everything with commas and semicolons at the front of their code, which is kind of a unique way to do things. I had actually not seen this approach except in this community post. but it's a nice way to basically start a line and indicate whether or not it's a continuation of an if statement or it's just another continuing statement of a compound expression. But other things you can see, they use emit sound to actually get the sounds playing. But otherwise, it's very just a logical progression of how you break a larger problem into smaller steps. They define a number of functions. They use scheduled tasks, which I will get to later on in more detail, and just other minor functions to, say, move the block or turn the block, etc. I think one of the main things to grasp from this code is that it's only a couple hundred lines, and you're able to get a fully qualified game that's more complicated than Pong, which was only maybe 10 lines of code. So it's amazing how much you can do in so little. So moving a little bit forward in time, if any of you have had a Windows system, you might be familiar with the game of Minesweeper, which was sort of standard in early Windows versions, although I don't think it comes with Windows 7 or Windows 10 or 95 anyway. So first, let's actually look at just what the game looks like when it's been ported into the Wolfram language. So I can actually pull that up separately, because the way this game was made, it was deployed as a CDF, which is another one of the technologies within the Wolfram technology stack. And what the CDF allows you to do is it's effectively a full version of Mathematica, just restricted to interactions within the front end. So a very nice way to distribute games. And so the interface is not quite the same thing as Minesweeper. Obviously, some of the details are different, but the game mechanics are the same. Where, again, this is a click pane, where if you click, it will distribute or clear the map of any open areas, but then also tell you where mines are located. And I think it's shift click, yeah. So if you hold the shift key down and then click, you can also flag mines that you know of, and eventually if you clear the map, you then win the game. So kind of a fun way to do things. But one of the challenges of this game is actually developing an algorithm that if you click in an empty space, that it will actually clear out and find all the remaining empty spaces. So that is also more detailed in this blog post. So this was actually, again, all credit goes to Benjamin. There's only a couple of games that I actually made in this talk. Everything else I'm actually pulling from our Wolfram community. So I won't go through a lot of detail because this is actually a very involved game, especially when it comes to figuring out which tiles should be automatically uncovered. But the basic idea is that you come up with a way to break the game down into the smallest pieces possible. And so the first question that the developer had is, I need a grid. How do I make a grid? And so this test grid is effectively just a matrix, but then thrown into the grid function to actually organize it in a nice grid arrangement where the spacing is uniform. And so basically just using the random function, in this case a random choice, in order to figure out which spaces to actually fill with mines. And then the next thing you have to determine is whether or not the spaces are safe or dangerous because they contain mines. And so again, just figuring out where in this grid the mines are indicated by just strings with M. And then because this is in a matrix, it's easy to test where your nearest neighbors are. You basically just shift your locations by 1 in any direction and then select for the ones in which you actually find the mines. And then once you've actually found the nearest neighbors, you can then count how many mines there are inside the nearest neighbors and then just create one of those, a table of those values. So that's basically the game mechanic in terms of just the back end of the game. But obviously you want to create a user interface, which I mentioned the Wolfram language is very good at. And so in this case, he actually creates a number of layers. and then eventually, I'll skip a couple of steps, ends up at a click pane. So this is the same functionality that I described in the point and click adventure a couple of slides ago. But in this case, the click pane is doing a lot more with its function. So you see its function, which starts with this bracket here, is actually doing quite a bit. It's testing whether or not the shift key is held down, so that's how you can flag a mine, and then it's actually replacing certain parts of the underlying grid. So, and the rest is sort of just icing on the cake. You know, you can add a win-lose condition. Basically, if you've clicked a mine, you've lost. And this is really, step 11 is the meat of this game, where you actually have to figure out how to automate the, I forgot what the actual technical term is, but it's basically like how water would flow through an area. You have to figure out which tiles would actually be automatically removed because they don't have any mines under them. And so this was actually kind of a longer piece of the code, which in the end is sort of like my understanding is it's a common algorithm to do this. So no more boring code. Let's get back to some games. So another thing that we can do is actually create a side scroller within the Wolfram language. So I hope if you're not impressed yet about all the different interfaces you can make in the Wolfram language, there is some music with this one. I don't know if you can hear it. I'll lower it just a little bit. But the point is, if I click on the interface, I can then move the character using the keyboard controls, in which you can actually whip and even jump around a little bit. And I'll go ahead and stop the music. So if no one's actually familiar, this is an original Nintendo game. So this is actually what the original Nintendo game looked like. You actually had additional features such as a score, hit points, the enemies in terms of like a final boss would have hit points. So I just decided this is a game that I made to sort of emulate some of the basic features without going into too much detail. So obviously I don't have a score or hit points in this. But let's look at actually what I did to create this side scroller. So the first thing that I did is I actually found a background image, and there's a lot of hobbyists who love classic video games, so finding things like this is not that difficult. I'm not an artist, so I probably would not be able to make something like this on my own. But I did find this online, and then the way that we will mimic side scrolling is this will act as a background image within the graphics, and then I will only take a fraction of the screen that will update based on the keyboard input. So said differently, I have a static background but a moving plot range. So the character itself, again, I find online because there are many hobbyists out there. So there's a couple of websites I have, such as the Sprite Database or Spriter's Resource. And you can find things that are so-called sprite maps. It's basically all of the animation screens for a given character. And so this is just one example for the game of Castlevania. And I've actually taken this upper right corner here to actually extract these different character screens and then kind of get them together into an animation. So what's great about this is the Wolfram language has so many tools at its disposal in order to make this relatively easy all in one interface. So the first thing I actually do is I image crop. So if you actually click on an image, see if I import this. I must not have imported this as a PNG. In any case, you can actually do, if this was an image, you could crop out certain elements of it. And so that's what I did here. I cropped out a couple of the animation cells. And then just using a couple of functions to remove the background and then crop the images, you see it's because these are very simple bitmap images, it did a really good job. And actually what makes a really good sprite map is to have a background color that is completely different from the character. And remove background figures out what that background color is and automatically removes it. And just to show, the image dimensions of these are truly very, very small images. So like 44 pixels by 29 is this first character. So you can do this for the rest of the characters. And then the difficulty, though, is that the characters, since I'm going to be using inset like they did in the Tetris game, to put these characters into a graphics object, the challenge is that you see here this flickering. The characters are not aligned because pixel by pixel, you see the squatting character is very much towards the left of its box, whereas the character I'm comparing with here is in the center of his box. And so what you can do is create an interface like this. I'm using the manipulate function in order to switch quickly back and forth between these two images until I can get them to line up. And so if I were to move this and add a certain amount of padding on each side, I can eventually get the two characters to align. And so now you see they're sort of flickering between the two. This isn't quite right yet because I should probably do something more like this. And so now you see the animation, the feet are effectively on the same plane, and now they're just flickering back and forth between those two cells. So this is basically one of the nice things is that I can use a very quick-made interface in order to basically normalize all of the graphics that I'm going to be using. Otherwise, the characters would kind of jump all over the place if I didn't have a normal predetermined size of every image. So in this case, every eventual image is going to be 105 by 42 pixels. The other nice thing about inset is all of the padding that I'm doing to these characters is going to effectively be transparent. So you can make all of the background pixels transparent, and so when you inset, you'll just see right through them. Let's stop that. So now that we have all of the sprites normalized in this workflow, the next thing I had to do was make sure the sprites were correctly sized, because keep in mind that the background image is relatively large, and if I naively just inset the characters, you see is going to be this tiny little character which does not really correspond with the size of the background I've chosen. So again, creating a simple manipulate in which I inset just a single frame, I can then create some sliders to move the character around and then resize him until I get a size that I want and a starting position, which in this case I'd want him to be just above the ground. And so that's, again, a nice way that the Wolfram language has everything at your disposal to quickly develop a nice user interface. And then just for some additional fun, you can find game music online. So either through, again, a sister site of the Sprite resource, or one of my favorites, this video game music headquarters. What's nice about this one is that all of the game music has been created into MIDI format, which is very easy for Mathematica to read in. And so that was the music that you heard playing originally. Otherwise, through the sound resource, you can actually import the WAV files and then play some of those. And I'll turn my speakers on to see if any of you recognize this sound. Not that, it's the Windows sound. That's the sound of the start button if you play a classic Nintendo game. Anyway, I think they're fun. I'm an old classic gamer. So in this case, the source code, again, is more involved. So I put everything into a package. I'm not going to go into detail about the source code because, again, this is not, if you really want details, you can look at this community post that I made. But basically, I need to localize everything so I don't leak into the global context. But the basic idea is that I first load in all of the predefined images, and then I load in the sounds that I'm going to be using, and then the main code is using a couple of event handlers just to basically track the keyboard keys, because what a keyboard key is actually is an event, a system-wide event. And so Mathematica has special sort of strings to indicate different keyboard keys. So there's a special left arrow key, which it basically tracks if the left arrow key is down, the right arrow key down and up, And then you can actually tell the Wolfram language to figure out which keyboard keys individually are being pressed. So I can basically use key down together with Z to indicate when I want to have this character use his whip, or a key down of X to make the character jump. Now you notice that in the game there is a bit of gravity. So if I show you here, there's the whipping and then the jumping, and the character does return back to the ground. And the way that I implement gravity in this game is using the scheduled task. And so what a scheduled task is, it's a task that runs asynchronously in the background of your Wolfram language session. And so again, I'm using just sort of Euclidean motion where I'm adding a constant value to the player's position. And in this case, gravity is simulated by just being a change in the velocity. And then the player's position in the vertical direction is just a change in that updated velocity. And I just make sure that the player doesn't fall through the ground. Instead, if the player is below the ground, I just reset his position to be the ground level. And so this scheduled task is actually currently running right now asynchronously in the background, such that anytime I hit the jump button, he falls back to the ground. But one of the things you might notice in this demo is that I don't control how many times you actually, let's see, where is that? The jump key. So every time you hit the jump key, the player's velocity is positive. So there's kind of a fun bug in this game that if I hold the jump key down, the character just flies off the top of the screen. The other thing to keep in mind if you actually are using the event handler with the event keys on the keyboard is that they are blocking, and this isn't exclusive to Mathematica, but if I were to hold an arrow key down and then try and jump, you see that the character's left and right motion is stopped. That's because when I hit the jump key, it cancels the motion in the other directions. So this is a sort of an annoyance. It's not, and again, this isn't limited to the Wolfram language. It's such a low-level event inside the operating system that it just blocks everything else. So the way to get around this is to actually use something that's non-blocking. And so what we can actually use is an external gamepad. So what I have here is an Xbox controller that you can't see, but the idea is that since I'm on a Windows machine, I'm using this Xbox controller because it's also made by Microsoft. But the Wolfram language has a lot of connected devices, and if there is a device driver already installed, oftentimes the Wolfram language can instantly detect it. So in this case, I already have the Xbox controller connected, and so if I use the function controller information, you can actually see that as I move the joysticks, you can't see me moving the joysticks, but you can see the changes being made, that you can actually update the buttons, and the Wolfram language understands that. So if you don't use the controller information function, again, you can use our dynamic functionality and ask for specific controller states, and now you can see X and Y is the left joystick, X2 and Y2 is the right joystick, X3 is the directional pad, which only has discrete values, -1, 0, and 1. And then you have all the different buttons that you can press, including bumpers and as well as slider buttons that actually can keep track of how far you've actually pressed the key. So I'm trying to press this key only about halfway down. So with no effort except plugging this controller into the USB port, Mathematica can instantly use it. And so we can use this to our advantage. In this case, I made a game here, which is, I'll remove some of the scheduled tasks from before. So I made a game that is sort of like a side-scroller, a modern side-scroller, although without any of the fancy graphics. So if you played games on the Super Nintendo, such as like Mega Man X, then you'll notice that the game is actually divided into a grid. And so it's a nice way to keep track of hit detection, which is a necessary element in a video game. That's why this character here, this two-tiled yellow block isn't falling through the ground, is because it actually knows there are these light blue elements below it. And so let me just make kind of a fun game. So what I've implemented is a double jump, so you can actually hit the jump key twice. And so that's necessary in order to get on top of the blocks here. Oh, can't quite make that one. So this is a combination of a sort of a click pane as well as some hit detection and some dynamic functionality. I still can't make that. Trust me, it's worth it in the end. So now this is a very simple game where I succeeded by exiting this trap by creating a number of different platforms to jump on. But again, what's kind of fun is if you escape the map, it'll just keep going because gravity just goes on forever. So anyway, I'll get rid of that. So what I want to demonstrate here again is just the simplicity of what you can do with inside the Wolfram language. So just to show some of the development steps, again, I mentioned that everything is broken up into a grid because checking the hit detection based on rectangles is very easy. And so I have some helper functions which basically remove or add a block whether or not I've clicked the mouse inside this click pane. And then the main game again, because it's involved, I put it inside a package in which I have my helper functions within the private context. And then the game itself, I sort of lied a little bit. This isn't a click pane. I'm actually using an event handler, but it's acting like a click pane because the only events I'm actually asking for is whether or not the mouse is moved or whether or not I've clicked or dragged. And like the previous game, I'm actually including gravity through a scheduled task again. But this is also where I use some of my hit detection, because basically I use the with statement to inject the value of your current location, and then I check whether or not you're within a box. So if you're within a box, then don't move into that location, but if you're otherwise in a playable location, then reset the player's location to that new place. And again, gravity is just a Euclidean addition of a change in velocity and position. But otherwise, the game just keeps track of being a simple graphic with a bunch of rectangular blocks that are inset, actually just directly using the graphic primitive of a rectangle. And then the character itself is just a darker orange set of blocks. So the other thing to notice here is that I'm using the controller state, like I showed on the previous slide, to basically take the input of the controller and use that to update the player's position. Now I'm using the directional pad on the controller, so I'm only updating either, -1, 0, or +1. And so the character is not moving at fractional distances. And then I just use a dynamic around the whole thing to make sure that the front end is updating these values as fast as possible. So, and again, probably just tens of lines of code, I'm able to create kind of a fun game where you can create your own map and then escape from it by jumping around. So because you can actually use a controller, a gamepad, to get around this blocking issue, I actually went back and redid my Castlevania demo. So I made it a little bit fancier and added some game elements, such as a start screen. I actually had my wife playtest this game, and the most annoying part was that it jumped you right into the game. And so it's kind of nice. Again, I'm using the Wolfram language to create this. I actually just inset a couple of text into here, but then if I actually start the game, I don't have any music anymore. But now the character can jump around, he can still whip, but now I actually have enemies that will die on screen when hit with the whip, and I actually use a lot of the random functionality. Uh-oh. So this is what I get when I'm trying to actually share the screen at the same time as doing a video game. No biggie. Okay. So I actually had that issue happen to me earlier. But the point is, if we actually look at some of the source code, which is in a separate notebook, this is a nice way to actually package up certain things, and I'll make this a little bigger. So if you're actually making extended packages, you can use an external integrated development environment such as Eclipse, but within the Wolfram language, you can actually open a new package editor environment, which I did here, that looks very similar to a notebook interface, except instead of input and output cells, you actually just have code cells. And then section cells allow you to collapse certain blocks of code to make readability easier for you. So very similar to the earlier game, the only difference is I added some additional features such as that initial loading screen. Okay, so another game that I made, and this was actually my first attempt at making games, is I ported the game of Flappy Bird. Now, if you aren't familiar with Flappy Bird, it was a game developed for the iOS and basically your cell phone, so it has this vertical orientation. But it's a very simple game that you control this bird Flappy, and you have to navigate through a set of pipes, and you earn points by correctly navigating the pipes. So this does have some annoying music to it, so I apologize. But I'll show the game first, just to get your curiosity. So again, I have a starting screen, which you will then click to start controlling Flappy. And then every time I hit the control key, Flappy flaps a little bit. So a very basic setup. I tried to keep it as close to the original implementation as possible in terms of the graphics, which I just cut from screen captures of the internet. But again, this shows just the versatility of the Wolfram language, that I was able to do all of this in just a couple of days. And now, albeit I did know the Wolfram language pretty well when I made this, but at the same time, it is quite nice that you can do so much with there's just so much built into the Wolfram language. So the first thing I did was just update or create a gravity-like environment, so using a basic graphics. If I click the jump key, you actually see the vertical position change quite rapidly, and this is again because Dynamic wants to update as fast as possible. And so to get around this, I actually set an update rate. I created a variable frames per second, FPS, which it was basically a way to limit how quickly things update. So using the scheduled task again to mimic gravity, I basically scale all changes in direction or acceleration by according factors of the frames per second variable. So in doing this, now if I click the jump key and I actually adjust what the values of the initial jump velocity are, you can get sort of a nice sort of jump action by choosing appropriate values. So again, I am using keyboard controls like in the side-scrolling demo, but I'm only using one keyboard control, which is the control key. What's nice about the control key is that it's a known key inside the Wolfram language, so you can just query its current value. So then if I actually hit the control key on the keyboard, I can change it from true to false. So this is sort of outside the event handler. It just knows whether or not the control key is held. The other thing that I do differently, so the character, like in my side scroller, just doesn't jump, outside the screen, is that I actually keep track of whether or not the previous button state was held. So using a very nice short switch, I basically say if you're going from false to true, so hitting the button for the first time is the only way that you can actually increase the vertical velocity. Otherwise, you don't do anything except reset the button. Again, introducing obstacles is rather easy to do. Again, using a simple manipulate, I'm going to be navigating pipes, but I can control how wide the pipes are, the spacing between the pipes, as well as the position, the relative position of the gap in the pipes. So in just a few lines of code, I'm able to actually figure out what pipe size I want for the screen size that I'm using, and then eventually create a function that creates a random sequence of pipes to navigate through. Instead of using blocks to create hit detection, instead what I'm actually doing is I'm using the region intersection function of the Wolfram language. There's a lot of built-in regions, such as disks, rectangles, circles, and other primitives. And what you see is that if regions are not intersecting, then the region intersection is effectively an empty region, in this case of 2 dimensions. But if you get these to overlap, you see that you actually get different kinds of intersecting regions. So that's how I implement hit detection. I basically have the character is going to be a circle, and the pipes are effectively just rectangles. And so if they overlap, then they're going to give me something that's not an empty region. And so that's how I implement hit detection in this game. And the rest is just icing on the cake. The game mechanics are already there. I have hit detection, and I've got control, including gravity. I don't really need to do much else besides move the pipes across the screen at some fixed rate. But I can also add additional images, and these are just screen captures I took off the internet and then sort of fit them together with yet another screen capture, the Flappy Bird. And so again, in a simple manipulate session, the hitboxes are the red outlines, and then the images themselves are just inset in there. But this is basically allowing me to figure out how big of, say, Flappy I want to do and how big of the pipes I want them to fit within the hitbox. And then I want Flappy to be a fair game. Flappy should actually be bigger than his hitbox. Otherwise, you'll get too many hits unnecessarily. And so this is, again, a way to size the sprites that I'm going to be inputting into the game. And lastly, animations are very easy to add just by getting this sequence of sprite cells. And so just taking a couple of screen captures, so the animation of Flappy is actually just 4 cells, and then you can get what appears to be a flying spherical bird. So in the game, I'm actually not using list animate. I am using other functionality to basically sequentially update the sprites, but it does give you the impression of animation. So I am sort of hand-waving a lot of the details because within the actual Flappy Bird code, I do other things to optimize. The main thing is actually reducing the size of the sprites. So if I were to screen capture something, because you see Flappy is just made up of pixels, and Flappy itself is probably just about maybe 30 pixels by 30. If I were to do a screen capture and then inset that into the game, I'm actually insetting a very high resolution image of a very low resolution thing. And so the first sort of advice I would give if you're going to approach it this way is to actually lower the resolution of everything that you're putting into the game, and then the game will actually run a lot smoother. That was the main bottleneck of this game, was I realized I had too high of resolution images, and it takes too long for the single CPU that Mathematica is running on to do all of the updates in real time. So the last game I want to demonstrate, again, I did not make this one. The game was taken verbatim from the Stack Exchange post, and actually the game was first made and shown on Stack Exchange, but we were so impressed by it we asked the author to also make a community post, which is part of our Wolfram family. So first I'm going to quit the kernel just to free up some space, because this is a game that's actually played in 3 dimensions, and hopefully on this computer I don't crash everything. It'll take a little bit of time to load, but what I want you to be impressed by is not only is it using parallel functionality to do some of the processing to get around the single CPU limitation, it also appears to be playing in a full screen mode. And I don't know if you've ever played Minecraft before, so it's not playing as well as it does on my laptop, but you actually get both forward motion using the keyboard keys WASD, and then the arrow keys will actually change your viewing orientation. But if I did get close enough to here, you see you can actually click on these blocks using an event handler. And again, it's not running very quickly on this machine, but if you click, you can destroy a block, and if you, I believe it's right-click, you can actually add a block, but the selection bar isn't actually appearing. There we go, I added this little cement block in the distance. So what's amazing is that you can actually even play Minecraft Classic, or a version of it, a ported version of it, within the Wolfram language. And even though I'm playing at full screen, this is actually still within a notebook. And I can show you that by actually getting out of the full screen mode. And you see this is still a Wolfram, a Mathematica notebook, which is quite impressive, I think. So you can make games that actually still look like games because they play at full screen. Anyway, that was the last game I wanted to demonstrate. I don't know if this notebook is going to be shared with the audience, but it does have a number of useful links if you want to, say, use these games as a starting point. I also have a couple of links of other so-called games. These are more like game solvers than actual games, but they are pretty fun.